This might be the last place you'd want to be, and yet it's entirely possible that you're already in it. This is potentially what your place of residence looks like. This doesn't just concern you personally, but also me, as well as the entire universe, which might currently be inside a black hole. To understand why, let's remember that for a black hole to form, you need to concentrate enough matter in a volume of space to curve the space-time continuum, to the point that nothing, not even light, can escape from it. However, that doesn't always mean a black hole is extremely dense. Because even though we tend to picture these perfectly opaque objects as small, compact holes, their size can be incredibly huge and their density extremely low. In theory, any object, no matter how small its mass, can become a black hole. By compressing your body's matter into a volume 1/10,000,000th the size of a proton, you would get a black hole. By compressing all the matter that makes up our planet into a volume about the size of a small marble, or the entire mass of the sun into a sphere about 3 kilometers in radius, each time you would get a black hole. The smallest black holes discovered in the cosmos so far contain something like 3 times the mass of the sun, in a sphere nearly 18 kilometers in diameter. It's still small, but we know of much larger black holes. Some with masses several thousand times that of our sun are almost as large as our planet. As for the most massive and largest black holes discovered in the universe, they have masses several billion times that of our sun and reach truly astronomical sizes, concentrating the mass of a small galaxy into a volume about the size of our solar system. And since the average density inside a black hole is inversely proportional to the square of its mass, the most supermassive of these objects have very low average densities, similar to water, while the most massive ones we know of, such as the black hole, Holborn 15A, whose mass is estimated to be 40 billion times that of our star, and with a radius of 118 billion kilometers, 20 times the Sun-Pluto average distance. Their densities are similar to air. Whereas if you filled a volume of space as vast as our solar system with air, you would get a black hole. That's extremely strange. Okay, let's continue the reasoning. In the interstellar medium, the near vacuum between stars, there is on average 1 atom per cubic centimeter. What would be the volume of space to fill with such an average density to form a black hole? The answer is a 30 million light-year diameter sphere. As a reminder, the Milky Way is 100,000 light-years across, so that's 300 times wider than our galaxy. If you filled this vast space with just 1 atom per cubic centimeter, it would become a black hole. Okay, let's continue with the reasoning. Hang on, it's going to get fascinating and a little unsettling. In intergalactic space, in the near vacuum between galaxies, there is on average the mass of 1 atom every 4 cubic meters. How much space would you need to fill with such a density to get a black hole? The answer is a volume with a radius of 25 billion light-years, which is about the size of the observable universe. Okay, that's extremely weird. In fact, if you added up the matter and energy of everything we can detect in the visible universe, you could get a black hole about the same size as the visible universe. Which means it's theoretically possible that our universe is nestled inside a gigantic black hole that could itself be in another, much larger universe. At this point, I imagine all of this still sounds pretty far-fetched to you. So, let me tell you about 2 surprising things that every black hole and our universe have in common. For a black hole, the visual boundary of the object, the beginning of absolute and total darkness, is what we call the event horizon. This boundary of the black hole's spatial extent marks the frontier between it and the rest of the universe, and whatever enters the hole will remain trapped there forever. Because beyond this kind of point of no return, gravity is so strong that you would have to move faster than light in a vacuum to escape. You may wonder how this relates to our universe. It also has an event horizon. Our universe is expanding, and this expansion of space has a strange consequence. Beyond a certain distance, galaxies in our observable universe move away from us faster than light. Knowing that nothing in the universe moves faster than light in a vacuum may seem counterintuitive, and it is. To understand this strangeness, remember this speed isn't about objects moving through space. It's the speed at which they move away from us. Because of the expansion of space itself, which separates them, expands, and stretches, like an elastic fabric would. In other words, it's the space on which the galaxies rest that swells and expands, carrying along everything it contains in its growth process. As a result, our observable universe has an event horizon. Everything that lies beyond this so-called cosmic event horizon is forever out of reach, forever inaccessible. Even if you had a hypothetical spacecraft capable of traveling at the speed of light to try to reach it. Because the distance separating us from the parts of the universe located beyond this event horizon is increasing far too quickly. In this sense, we are trapped within this horizon. Our observable universe, just like a black hole, is a place from which it is strictly impossible for us to escape. Okay, but what if the total mass of all the matter between us and the limits of the observable universe is, as a first approximation, enough to form a black hole? So why isn't everything in the visible universe being pulled toward the center, toward us? Well, first of all, the universe doesn't have a center. I'll refer you to this episode. On large scales, gravity clumps matter together, but this is balanced by the universe's accelerating expansion. Whereas, in a black hole, all matter will inevitably be carried away by the movement of a space-time conveyor belt, moving too fast to be counterbalanced, until it eventually reaches the center, where it is believed that a singularity sits, a ridiculously small region shrouded in deep mystery, where densities reach extremes, to the point where the properties of matter, energy, and even the distortions of space-time are pushed to their absolute limits, degenerating into infinity. That's the second thing they share. Singularities exist only at black hole centers and in our universe's distant past. Pick a random spot in the cosmos and point to it. The same kind of hellish conditions that exist at the center of black holes also occurred exactly where you're pointing, as well as everywhere else. Because every part of the universe experienced this in its earliest moments. At a time in the distant past, at the moment of the Big Bang, the same kinds of conditions that exist at the heart of black holes prevailed. One of the main differences between the singularities at the beginning of the universe and those of black holes is that, in one case, they involve the entire universe in the past. In the other case, they are precisely located at the center of black holes and involve only matter that has crossed the event horizon, and for which these singularities represent the only future, the only possible destiny ahead. Today, the singularities of black holes, like those of the Big Bang, represent insurmountable limits where our knowledge collapses. Beyond that, space becomes infinite and loses continuity. It's unknown. We're still seeking a theory that unifies quantum physics and general relativity to explain the behavior of a crumpled time. And even if it turns out one day that nothing links black holes and the Big Bang, they still have things in common. They are extreme laboratories that galvanize minds and theories. By studying the similarities between the extreme conditions at the center of black holes and those likely present at the universe's beginning. That some physicists have come to wonder if the two phenomena might be connected. If the Big Bang couldn't in some way be the result of a kind of inverted and unreasonably gigantic black hole. In any case, this hypothesis, which remains completely speculative, seems extremely difficult to prove. Because the inside of a massive black hole, like one with millions of billions of suns, is impossible to distinguish from a universe for someone inside it. Okay, so maybe this is the inside of a black hole. On the other hand, one thing is certain if we are currently inside a black hole. There should come a day when the expansion of the universe curled up inside should eventually be stopped by a kind of impassable wall set by the spatial limits of the black hole. I like the idea that you and I are both inside a gigantic black hole. A black hole we can observe from inside, containing living beings. Wondering if this black hole could be in a much larger universe, filled with other drifting black holes and beings curious about what lies within these dark stars. They also suggest their universe might be a black hole inside a larger universe containing many other drifting black holes. Living beings also wonder what secrets lie in these dark stars, while also raising on their side the possibility that their universe is actually a black hole nestled in a larger universe. You get the idea. It's absolutely mind-blowing, and it should, I hope, leave a few gaping holes in the back of your head. In an upcoming episode devoted exclusively to this disturbing possibility. Because until then, I personally need to let my brain cool down a bit.